You guys are on text page 168. Oh, what's your blue notebook page? Blue notebook 275. 9. Oh, sorry. 279. Okay, these are the definitions. We're moving into quadratic relations today. So you guys are going to learn about what a quadratic relation is and how we represent it with numbers. Learn about what a parabola is, the vertex of a parabola, the axis of symmetry in a parabola, how to tell something's quadratic by looking at finite differences. There's quite a bit we're going to have to cover today, okay guys? So, very first thing we're going to deal with is we're going to call it our theoretical model, okay? A theoretical model of what a quadratic relation is. So y is equal to, I'm going to put things in special colors so we can separate them. Y is equal to 8x squared plus bx plus c. Okay? Now, the idea behind this is very similar to what you guys learned in grade 9. It's just a different shape. You guys had learned about linear relations. You had your y is equal to mx plus b. In that case, x was to the power of what? Anyone know? 1. That's right. Okay? So this m and this b could be any number. And because the exponent was to the power of 1, it made it a straight line. That's the shape it would make on a graph. Today you guys are learning this is called a quadratic relation. Okay? So this equation here, that equation there is a quadratic relation. A, B, and C can be any possible number, okay? As long as we have an exponent to the power of 2, okay? That's going to give us a parabola shape, and we're going to get into that later. What we're going to do right now is I'm just going to give you some quick examples of this, just to get it into your head, okay? Y equals x squared plus x plus 1. Is this quadratic or linear? This is quadratic. Even though this x here is to the power of 1, there is an exponent to the power of 2. That's very important. That automatically makes it a quadratic relation, as long as that's the highest exponent. Okay, and that's what those are the highest ones we're going to start dealing with today. Just like this equation here. In this case, what was A? 1. That's right. A is 1. What was B? And what was C? Look at that. 1, 1, 1. All right? It could be any number. That was just an example. How about this one here? Y is equal to 3x squared minus 2x minus 5. Quadratic or linear? Quadratic. That's right. A is what value? B is negative 2. And C is negative 5. Good. This is a quadratic relation. Excellent. All right. Let's try another. Quadratic or non-quadratic? Do a vote. This is a quadratic relation. This is quadratic once again because we have a variable to the exponent of 2. As soon as we have a variable to the exponent of 2, assuming that's the highest variable of exponent, like it is in this case, it's automatically quadratic. What is the value of A? 1. What's the value of C? Negative 5. Here's the trick. What would the value of our B be in this case here? 0. When B is 0, what is 0 times x? 0. It just eliminates that x. It doesn't make this not quadratic anymore. All it does is our value for B is 0. Okay? So that one works fine. How about this one here? Quadratic or linear? Quadratic, that's right. This is quadratic because our variable, once again, is to the exponent of 2. What's our value of A? 1. Value of B? Value of C. That's right, they're both 0. That's the B at x, blah, 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 blah. Okay, good. Like I said, they could be any number. Now, here's a little different. I give it away, but what about this? Quadratic or non-quadratic? Non-quadratic. And why is that? Yeah, what's the exponent to? 1. That's right. What is this then? What would you call this relationship? Not a quadratic relationship, but a linear, like in grade 9, right? The exponent's to 1. This is linear. Good. What happened there, and this is the only way, if A is equal to 0, it's no longer quadratic. Okay? B and C can be equal to 0, that's fine. If A is equal to 0, it negates our variable to the power of 2, and it can no longer be quadratic, because it's getting rid of our exponent to the variable 2, and then our exponent is then to the variable 1. Okay? So it gets rid of that. It's no longer a parabola. Okay, good. So you guys have gone through some examples. Okay, so we've dealt with the quadratic relationship in a theoretical form. We have our numbers represented. Now we're going to show what it looks like on a graph. Oh, shoot. Okay, so like I said, we're going to start representing quadratic relations on a graph. So a quadratic relation on a graph, and I'm going to connect it to an actual numeric value. I'm going to give you an expression. We're going to use this one, y equals x squared. Now, I don't expect you guys to know how to draw this at all. I'm just going to draw it quickly for you. Okay? But oops, I've drawn that wrong already. Yes, we're going to be making almost like a U shape. Okay? On here? This shape represents a quadratic expression. Now, this shape can look many different ways. Like I said, this quadratic, we'll call this is called a parabola. When it's drawn on a graph, it's a U shape. This could be U-shaped upwards. It could be downwards. It could be in all different areas of the graph. We could get one here that looks very thin. Okay? If you get one that's going the other way, it could be very wide. Okay? All of these are parabolas. There's different versions of them, and we'll learn later how to represent them with numbers. The black one is represented as y equals x squared. These other ones all have different numbers involved for A, B, and C. Okay? These are all quadratic or all parabolas. So all of these lovely U-shaped objects I've drawn, they're all parabolas, every single one of these. They just look different. Now, what we're going to learn is, I'm going to get rid of the other ones. We're going to learn how certain points of them have names. Certain points on the parabola have a name. This point here is the lowest point of this specific parabola. This lowest point is called the vertex. Okay? Now the vertex represents the lowest or the highest point. So if we had a parabola that is facing downwards, yes, that's right. This would be the highest point, and it is also known as the vertex. Okay? So the lowest or highest point, which we're also going to refer to as the max or the minimum of the parabola. Those points are always our vertex. So it's either the highest or the lowest point of the parabola. Okay? It depends how it's facing, upwards or downwards. We'll get a couple of minutes. Okay, so this lowest point here, because this is the lowest point, because that's the lowest point, that is considered to have a minimum. That would be the minimum of that parabola. And on this one, because it's the highest point, this parabola has a maximum. You can only either have a minimum or a maximum. You cannot have both on these parabolas that we're drawing. Okay? So, in this one, it's facing upwards. Anytime a parabola opens upwards, it's going to have a minimum, and that minimum is where the vertex is going to be. Okay? So this is our minimum, because it's facing upwards, and that is exactly where the vertex is located. Now this parabola here is facing downwards. This parabola has a maximum, and that's where the vertex is going to be, right at this specific spot. Okay? Okay, and finally, we're going to talk about an axis of symmetry. Now, it's important that you know the axis of symmetry goes right through the point of the vertex on any parabola. So, on this first parabola we've drawn, my axis of symmetry is a straight line going right through the middle of this parabola. Now, obviously, with my shaky hands, my dexterity is imperfect, the axis of symmetry, you can kind of consider it a mirror image. The right side is going to be a mirror image to the left side, and it's going to be flipped or folded in half at the axis of symmetry. The axis of symmetry, like we said, goes right through the vertex. So on our other parabola, our axis of symmetry is going to be right here. I don't know why I drew that little extra one there. Get rid of that. Okay? Our axis of symmetry is there. It's a straight line through the middle of the parabola. Axis of symmetry will always go through the vertex and the max or the min, depending if the parabola is going upwards or downwards. So, for instance, okay, so they've given us an example. They've given us some coordinates. Our x coordinates are -2, -1, 0, 1, 2. The y coordinates that relate to those are 4, 2, 0, 2, 1. So we've written them down on an xy table. Okay? By coordinates, without graphing anything, we're going to try to figure out if it is quadratic or non-quadratic. Okay? And the way to do this is we need to find the differences of our y values. So first of all, we're going to have to find the first differences. And first differences, okay, first differences, if they're the same, means we have a linear equation, okay? If second differences are the same, that means we have a quadratic relationship, okay? And I'm just going to make one change to these numbers because I wrote them down wrong. Sorry about that. I changed the numbers. It's 4, 1, 0, 1, and 4. Okay, so we're going to find the first differences. And what that means is I take my top y value and I subtract it by the one below it. So we have 4 subtract 1. What is that going to become? 3. Good. Okay. The next first difference I have, I take the top y value again, subtract by the one below it. So I have 1 subtract 0. What am I getting? 1. Same idea. 0 subtract 1. What is the difference? -1. And 1 subtract 4. What does that give us? -3. Okay, are the first differences all the same? No. Our first differences, we have 3, 1, -1, and -3. Those are our first differences. Cool, eh? Those are not the same, so it's not a linear equation, okay? So we know it's not linear, which means it's not a straight line when we go to graph it. So we're going to find the differences of those differences. They're called second differences. So I'm going to find my second differences. I take my 3, subtract 1, 2. It's the same idea. I take this difference, subtract by this one. I take 1, subtract -1. 1, subtract -1. What do we get? 2. -1, subtract -3. 2. Okay. Second differences. Were the second differences the same? Yes. They're all 2, which means we have a quadratic relationship. It's as simple as that. We write the coordinates down, our x and our y in our xy table. We find the differences of our y values. If the first differences are the same, then it's linear. So I'll just write that underneath so you know. Then if those are the same, linear. But they're not the same in this case. If our second differences are the same, it's a quadratic relationship, which means when we go to graph it, we'll draw a parabola on a graph. Now, if second differences aren't the same, that means it's not linear and it's not quadratic. That's your homework. Blue Notebook, page 281 is telling you to do these questions on 172, 1, 3, 4, 7, 10.